All right, welcome back everyone. We have 7.1 transforming exponential functions. Make sure to support the channel, like and subscribe, help my ideas get out there. I've actually gotten a lot of interesting comments, especially in my computer science videos, and it's really helping me learn how to be a better teacher. Now, you have two learning goals. You have the first learning goal to transform exponential functions, and two, to analyze growth and decay functions. Now, this is a refresh, okay? And I'm highlighting that this is a refresh because you should have seen exponential functions already. This is tailored to Algebra 2 students. So we are going to refresh on it, but we're not going to break it down from its absolute most basic form again, okay? So what makes a exponential function special is the fact, and let's write the most simple version above, is that you're going to have a base number to the power of x, okay? If you look at all the other functions that we've looked at so far, right, you could have, let's see, y equals x, right? So your x is a base number. It's not an exponent. You could have y is equal to x squared. You could have y is equal to 1 over x. You could have y is equal to x to the power of 3, right? These are all functions that we've looked at, all right? But notice how this is the first time that your unknown, right, your input variable is in the exponent's place, all right? That's where your change is. That's what makes this exponential, all right? Hence the name, right? Your x is in the exponent's place, exponential, okay? Now, these break down. We're going to graph these by transformations, and it breaks down just like every other function you have learned. And that's the real reason why we transform with all of them, because once you learn how to transform one of them, it becomes very easy to transform another. So your a value, just like always, is going to be your stretch. Let's change this to something smaller here. Okay. It's going to be your stretch, and it's going to give you your compression, and it's going to give you your reflection. And it's the same type of values that do that. If it's greater than 1, you get to stretch. If it's between, 0 and 1, okay, then it's compression. And if it's negative, you get reflection, all right? Now remember, the stretch and compression has nothing to do with the negative number. You ignore it for the stretch and compression. The negative only tells you about reflection, okay? Now you have a base number here, that's b, okay? And your base number is actually going to do something very interesting to the problem, okay? And I'm going to wait to talk about this one because I want you to see it as we do it, but it is going to change the graph a certain way, okay? And then your h and your k work the same exact way. Your h will translate it left and right, okay? And let's do, if it's positive, it goes left, and if it's negative, it goes right. So hopefully you can see that here. Positive makes it go left, negative makes it go right. Okay, just like all the other ones, all right? And then k is the same way. That gives us our up and down, all right? So yeah, this was, we'll go up, and then we'll use d for down. And up is when it's positive, and down is when it's negative, just like every other time we have done this, okay? So that's your refresh. We're focusing on the same ways of transforming. Okay, and then also, quick highlight. This is the most basic form you can have. If you have a number to the power of x, you have the most basic exponential. And that actually really highlights, a question that we have here. What is the parent function for an exponential? Because all your other parent functions we wrote here. It was x to the power of something, or 1 over x. But now x is in the exponent's place, which means, which means, what is our base number for the parent function? And this is where things get weird, because I could sit here and I could say, f of x equals 2 to the power of x. I could sit here and say f of x equals 3 to the power of x. And those are still in the most basic form. I could even sit here and say f of x is equal to 1/2 to the power of x. Or I could sit here and say f of x is equal to 1/3 to the power of x, right? So what I'm trying to highlight here is that for all these other functions, these ones right here, you had one parent function. For exponentials, because we can have a different base number and it's still in its most basic form, we have an infinite amount of parent functions, okay? So when you're doing this, your parent function will start off with whatever the base number is to the power of x, and that will change what your parent function looks like just slightly, okay? So we have many different parent functions. So that will be our first step, and then we'll look at a values, and then we'll look at h and k, okay? So let's go right into doing one, okay? I'm just going to kind of write some things off the bat here. We have base 2, so this is our, kind of our parent function right here. So I'm going to go like this. That's our parent function. We have a stretch by a factor of 2, okay? And then we're going to have, let's see, all right, horizontally translated to the right 3. And then we're going to even see a vertical translation up 5, okay? Broken down pretty much the same exact way. But where do we start? What are our points? We have to figure out the parent function points every single time. It's not like the other functions where we can just sit here and go, these are our parent points every time, okay? So you're going to make a t-chart. We're going to go x and y. And for your x values, you should take -1, 0, and 1 to start off, okay? Those are going to give you a really good picture of how it looks to the left and to the right. And honestly, I still feel like that's not enough. I'm going to say do this, okay? I'm going to say, start off with -1, 0, and 1. But if you need more, a better picture, add in the -2 and the 2, okay? And so we're going to plug these in to just the parent function part, which is 2 to the power of x, okay? So let's do that right here, for our work. We're going to get 2 to the power of -2. Well, we remember with negative exponents, we have to shift it to the bottom. So it's 1 over 2 to the power of positive 2 now, and 2 to the power of 2 is just 4. So we get 1 over 4. That's our first point. -2, comma, 1/4. We do it again. 2 to the power of -1. Okay. We get 1 over 2. We get 1/2. We do it with 0. 2 to the power of 0. That's just 1. We circle these so we can see them. We do 2 to the power of 1, which is just 2. And then we're going to do 2 to the power of 2, which is just 4. Notice the pattern here again, right? We're seeing the same numbers here that we are seeing here. For our parent function, they're just, fraction versions, okay? So let's go plot our points. I'm going to do -2, 1/4, which is about here. -1/2. I'm going to do 0, 1. I'm going to do 1, 2. And then I'm going to do 2, 4. Okay? Now, if you think about if we only did -1 to 1, that's all we would have, and it would be very hard to kind of see that it is tapering off here, okay? And that it is just really going up. So I would add those in, honestly, I would do all 5 of those points. I feel like it's a better picture, okay? So this to the right here, it's just going to be increasing, right? Because if you keep this going, we get 8, 16, 32. And then if we keep this going in the other direction, we get 1/8, right? 1/16, 1/32, okay? So there is a horizontal asymptote here, okay, where it cannot cross. But I'm going to take that out because we are going to have to transform this, all right? But that's what your parent function would look like, all right? Now we're going to go to all those y values, and we're going to apply our a next, okay? So we're going to stretch it by a factor of 2. So let's look at these points, right? We have 4, 2, 1. We got 1/2. And then we have 1/4, okay? So we come through and we're going to multiply all of these by 2, okay? Which should make this rise faster, right? We get 8, 4, 2, 1, and then 1/2. You see how it kind of bumped them all up, right? Okay, so let's go in and put in our new points. We're going to have 8. So 5, 6, 7, 8. We're going to have 4. We're going to have 2. We're going to have, where are we at here? 1, and then a half. Kind of just doubled them all. Look at that, multiplied by 2, right? Okay. Next, we're going to do our horizontal and our vertical translation, right? So we're moving right 3, because remember, it's minus. So we're going to the right, and then up 5. So I'm just going to go to each point, and I'm going to go right 3, up 5. Now this one will go off, and that's okay. All right? So I'm doing these ones in green, so right 3, up 5. Wow, that way goes off. I can't even write up there, so we're just not going to write that one. Then this one, right 3, so 1, 2, 3, 1, 2, 3, 4, 5. So my new point is there. And I'm going to do that for the other ones. Right 3, up 5, right? Right 3, where is that? 3, 1, 2, 3, 4, 5. Right 3, 1, 2, 3, 4, 5. Okay? And I should also see that that asymptote that was at 0 moved up 5 spaces also. And I'm going to do this in blue. Okay? So my new function right up here, and then it's going to taper off at that asymptote. And it's going to go up, you know, and just constantly get bigger and bigger and bigger and bigger. Okay? Now, we have a lot of things to look at here, right? You know, we still have domain and range questions that we can ask, right? So domain. We have range. We want to see what the asymptote is, which here it's horizontal asymptote. Okay, and then we also want to know what the y-intercept is, all right? And all of these can really be looked at by observation. If you look at your exponential function and you think of domain, it's forever going to the left, it's forever going to the right, so your domain is all real numbers, okay? Then you have your range, which is really getting cut off here by your asymptote, so it's everything y is greater than or equal to 5. Not equal or equal to, sorry, just y is greater than 5 because it can't equal 5. Your asymptote is a horizontal line, so that's y is equal to 5. And your y-intercept crosses right here. Now that was at a half, okay? Because here we were at a half, and we went over, oh no. Oh, okay, no. This one was at a half, right? And so we went over 3, and we went up. Well, the next one would have been at a fourth if we followed that pattern. So this would be at a fourth also. So that'll be 5 and 1/4. Okay, so 0, 5 and 1/4. Okay, now if you're like, what? Mr. Fair, 5 and 1/4, can you please explain that again? In class, you'd be able to ask that question, but right now you can't, right? Remember, if you want to calculate this perfectly, you can always just go to your function, plug in a 0, and solve, and you get the y-intercept. Okay, so if you can't see it on the graph, plug it into the equation. Okay, so this is exponential functions. Notice this. When we had a b value that was greater than 1, we started low and we went high. Okay, so let's go back a page here and let's write that in. Okay, if our b is greater than 1, our function starts low and goes high. Okay, now going back to the next problem here, this is a u-do. I know there is a half here, okay? And I know you can do a half. You can take 1/2 to the power of x, okay? Because that's your parent function. When you do the parent function part, you forget about this +1. So I want you to try this, make your t-chart, okay? Plot it, transform it, give me those same 4 things, okay? So I want to know what your, let's see, I want to know what your domain is. I want to know your range. I want to know the asymptote. Forgetting a p somewhere in there, okay? And I want to know your y-intercept, okay? All those 4 things. So pause it, give it a try, and then I'll go over it. Okay, so hopefully you guys got that, all right? You would need to make a t-chart off the bat, all right? and you're just going to use the 1/2 to the power of x. That is your parent function for this one. So parent function. Okay? Now, I'm going to suggest that you use -2, -1, 0, 1, and 2 as your points. Okay? It just gives you a better picture. So let's start this off. We're going to have 1/2 to the power of -2. Now, you may have gotten to this and been like, what now? Right? But if you have a fraction to the power, you're really just taking it and applying it to each, right? And if you have a negative exponent on the top, it goes to the bottom. And if you have a negative exponent on the bottom, it goes to the top. So it becomes this. And then 2 squared is just 4, 1 squared is just 1, so it's 4 over 1 or just 4. Okay? Now, you do it again for -1. 1/2 to the power of -1 equals, let's see, 1 to the power of -1 over 2 to the power of -1. They flip. Oh, whoa. They flip. There we go. We get 2 over 1 or just 2. Okay? Now, sorry, my work is not really lining up here, but then we got 0. 1/2 to the power of 0. Anything to the power of 0 is just 1. And then we have 1/2 to the power of 1. And we do the same thing. We bring it in. 1 to the power of 1 over 2 to the power of 1, which just becomes 1/2. And then we have 1/2 to the power of 2, which we apply it again. We get 1 over 4. All right? Now notice how this is trending in the opposite direction. Okay? If we go back to this one, we started off low with fractions and we went high. On this one, because there's a fraction and because we're going to see this negative flip here, we start high and end up going low. So at -2, my point is 4. At -1, my point is 2. At 0, my point is 1. And at 1, my point is 1/2. And at 2, my point is 1/4. We're going high to low. Okay, so let's just go back here for a second and let's finish looking at that b value. If b is between 0 and 1, it flips. We go high to low. So you're going to see that that b value is going to change whether we're going to grow in values or whether we're going to decay in values, which is going to be our next point after we finish this problem. Okay, so let me take, oh dang it, my undo is going on all the previous pages. There we go. Okay. All right. Now, we need to stretch these points. This stretches by a factor of 3, so we're not seeing any compression here. But, you know, again, if you would have had a 1/3 there, you'd have to multiply by a third. Okay. We're also not seeing any negative values there, but you need to remember, if you had a negative value there, all it would do is flip it over the y-axis. Okay. So I'm going to go to all these points. All right. Let me actually reduce size this even a little bit more. There we go. Okay. We're going to have 4 times 3. We're going to have 2 times 3. We're going to have 1 times 3. We're going to have 1/2 times 3. And we're going to have 1/4 times 3. Okay. So we're going to get 12, 6, 3. 1/2 times 3 is going to give us 3 over 2, so or just 1.5. And then 1/4 times 3 is going to give us 3/4. Okay, so let's do all those points in blue. 12 is going to be off, but right here would be 10, 11. So we'll just call this 12. I know that's hard to see. Okay, and it's a little truncated, but it would kind of make it on our graph. Okay, 12. Then we have 6. And then we have 3. Okay. Then we have 3/2, which remember is just 1.5. Then we have 3/4, so it's kind of like 0.75 right there. All right. Now we look up here. We have a +1, so that's left 1. And we have a -1, so that's down 1. So we're going left 1 and we're going down 1. Okay. We're going to do that in red. So left 1, down 1. So left 1, down 1 here puts me at 11. Left 1, down 1 puts me at 5. Left 1, down 1 puts me on over here. Left 1, down 1. Okay, left 1, down 1. Okay, so we're going to draw this. Well, actually, let's do our asymptote, right? So the asymptote shifts by going up and down, so it moved down -1, so we should be tapering off here. Okay, let's erase this work. So in red, we're starting high. Could do that better. And going low. Okay, now domain, very similar, right? All real numbers. We're forever going to the left and right. Range, we move down, so we have all the way down to -1. We're still above it because we didn't reflect, so y is greater than -1. Your asymptote is y is equal to -1. And your y-intercept, this one's easier to observe, right? We could see it right here. It was at the half before, it went down to a half again, so it is 0, 0.5. Okay, now this is transforming quadratics. You are going to have to do a t-chart pretty much every single time to find those initial points, okay? Now, we're going to pause. We're going to do a quick Desmos exploration, look at a little bit of that reflection. It'll be quick, and then we're going to get to growth and decay. Okay, so here we have it at Desmos, right? We see that we only have a straight line. We have our formula at the top left, y is equal to a times b to the power of x minus h plus k. And because everything is at 1, we're getting this straight line right now, okay? So let's change b to a number at 2, okay? And we can see that, you see how it's never crossing that axis, okay? And it's increasing in value very, very rapidly, okay? In fact, it's actually not crossing 1 because our k is at 1. So let's bring that down to 0. Let's bring h to 0. So we have a parent function, okay? So at a, if we increase a's value, you can see that it's rising. It's rising in value really, really, really fast. If we decrease its value between 0 and 1, we see that it expands, okay? Now when we get to negatives, look how it's doing the opposite. It's going down. Now I know we didn't do any examples with negatives, so there's your, kind of your example. It's going to flip it, okay? All right, let's bring this back to 1. Whoops, 1. Now for h, well, it's at 0.9, close enough. With h, you see if we go positive h values, which would write it as a minus in the problem, and go to the right, and as we go to the negative values, which would write it as a plus in the problem, we go to the left, okay? And then for h, we increase, it goes up. We decrease, it goes down, okay? So I don't know how you guys feel about these Desmos explorations. Please let me know in the feedback or comments. So, maybe this is pointless to do after. Maybe I should do it before. Just let me know. Okay, so let's bring it back. Let's do growth and decay, and then let's wrap this up. All right, so bringing this back, we have growth and decay. This is a refresh. You should have seen this in Algebra 1, okay? These are all exponential functions that you've already done, this was a growth, right? This was a decay, because if we read it from left to right, we're starting low on this one, going high, that's growth. We're starting high on this one and going low, that's decay. But generally you see them written this way because we deal with a lot of percentages in the real world with growth and decay, right? You buy this stock, it hopefully increases in money, but it could decrease by a percentage point year over year, okay? And so the way we write these is we still have A, which is our initial value, okay? We have R, which is our rate, okay? And you can see it over here too, rate, and you can see it over here, initial value. Okay, let's just do IV, okay. All right, the last thing is T, which stands for time. And this could be written, and we can do this monthly, yearly, it depends on the way the problem writes, what that time will represent, okay? But the big difference you're seeing here is that we have a plus R and that we have a minus R over here, okay? So let's break down when to use each one, okay? Because you're always going to put a positive R in there, and then you're going to either minus it if it's decreasing, you're going to add it if it's increasing, okay? Now, to model the left one real quick, if I said that we had a car that was worth $5,000, cheap car, right? And its value, nope, car would be for the other one. Let's do this again. Okay, let's say you had $1,000 and you invested in the stock market and you got a 5% return year over year, okay? Well, you can't put 5% in the problem, so we would need to put that as a decimal, 0.05, Okay, and we can't put $1,000 in as our initial. So the way we would write our equation is y is equal to our initial value of 1,000 times 1 plus 0.05, because we're increasing to the power of t. Okay. Now, you would simplify and you go y is equal to 1,000 times 1.05 to the power of t. Okay. So this 5%, we knew it is increasing because we were gaining money. We convert it to a decimal and we throw it in for rate. Because we knew we were increasing, we used this one with the plus sign, not that one with the minus. Okay. Now, why do we have this 1 in here? This 1 helps keep the initial value in the problem. If we did and just put a rate of 0.05 in here, well, 1,000 times 0.05 reduces it by 95%. We need to have this so we get the initial value, right? And then if you distribute again, you get the change, okay? And this would be compounded, by whatever time. Now, decay is going to be the same thing. Let's say I have a $20,000 car. It decreases at a rate of 25% each year, right? So I go y is equal to 20,000 times 1 minus 0.25 to the power t. I simplify, and I get 0.75 t, okay? That's how you do these, all right? So let's do an actual problem here so we can see what it's like, okay? The value of a mountain bike Y in dollars when purchased was $2,000. After riding the bike, the value decreases at a rate of 25% each year, where t is the number of years since the bike was new, okay? A, tell whether the model represents exponential growth or exponential decay and create a function that models it. Okay, well, if we are buying a bike, right, and we see that it decreases at a rate of 25%, we know that this is going to be decay. Okay. Now we want to identify those values, right? We had our A, which is our initial value of $2,000. Okay. We have our R, which is 25%, but we should really just write it as 0.25. Okay. Now we go to write our equation. Y is equal to, oh, no, it was 2,000. Okay. 2,000 times 1, and we're going to use the 1 with the minus because this is decreasing, minus 0.25 to the power of t. We simplify, we get y is equal to 2,000 times 0.75 to the power of t. Very similar that we did. The next step is we want to graph this, okay? Now with graphing this, it's a little bit more tricky, right? Because we have a lot of numbers here that are hard to calculate by hand, okay? So I will be using a calculator to do this, okay? And I'm going to plug in, I'm going to do the first 5, okay? And if we need more to get to 500, we can do that, all right? So I'm going to do a T chart, right? I'm going to go T and Y. In fact, let's do that over here. I can get a little bit more space, T and Y. All right? And I'm going to plug in my first one of 0. Now this one we don't really need a calculator for, right? Because if we take 0 here, 0.75 to the power of 0 is just 1, times 2,000 is just 2,000 again. So I don't need a calculator for that. Now the time, which this is numbers of years, so we're doing 1 year, okay? And I'm going to plug that in. So I'm going to go 0.75, all right? And I'm doing this on the calculator to the power of 1, which we know is just going to be 0.75 again, times our initial value of 2,000, gives us 1,500. Okay? Then I'm going to do this with 2. So I'm going to go 0.75 to the power of 2 equals 0.5625, and then I take that and I times it by 2,000. So that's 1,125. Okay, then I'm going to do it for 3. So I'm going to take 0.75 to the power of 3, I get a number, and I times it by our initial value of 2,000. Okay, I get 843.75. Guess what? We're going to do this 2 more times. 0.75 to the power of 4 gives me a number times our initial value, and I get 632.8125, which you don't have to write all the rest of that. You can round that to the hundreds. And then we're going to do 5. Okay, so 0.75 to the power of 5 equals a number times 2,000 gives me $474, and we're going to round that to 61 cents. Okay, now we kind of have enough to answer C, but we do need to go and graph this, and those are all of our points. Okay, so we need to label our graph here. We have Y. This is going to be money in dollars. Okay, and then we have our X, which we're just going to change this to T, and this is going to be the number of years. Okay, I'm going to skip 2 for years. I'm going to 1, 2, 3, 4, and 5. Okay, we can just call that 6 and 7. All right, and then on the left here, we need to get up to 2,000. So by every 5, I'm just going to go up. No, that won't be enough. Let's do this by 250 every 2. So 250, 500, 750, 1,000, 1,250. Are we going to make it? 1,500. I think we're going to 1,750 and 2,000. Okay, which of course I could have listed a little bit differently, right? So our first point is 0, 2,000. We're doing this in green. That's right up here. Okay. Then we have 1, 1,500. Then we have 2 and 1,125. It's about here. Okay. Then we have 3 and 843. We're just going to have to estimate about there. 4, 632. It's about there. 5 and 474. It's going to be about there. So it's hard to see the pattern, but it is kind of going, and it's going to start to curve off. Okay. Now for C, estimate the value of the bike, or estimate the value of the bike will be $500. Yeah, estimate when the value of the bike will be 500. Okay. So we're looking here, and we can see 500 is about here. And so it's kind of at about 4.5 years, although the line is not drawn perfectly. It looks like it actually might have needed to curve out a little bit, but we can say a couple things. We can say, between 4 and 5 years, okay? Or we can say stuff like close to 5 years, all right? But before. Or like right before 5 years. That's the kind of stuff that we can say for these types of problems, okay? So I hope that this was helpful. Okay. This is growth and decay. I did have a you-do, but I think that we're just kind of over time here. This is a really long video. So I'm gonna show you this problem. If you want to do it and ask questions before class, you feel like you need to practice, go for it. This is a growth one, not a decay one. But if not, that's okay. We'll get practice in class. All right. So thanks for listening, and I will talk to you guys next time.